into part 2 of atmospheric pollution. We're going to look into photochemical smog and thermal inversions in this one. So again, here is your essential knowledge. Take a look, take a look. So in order to really understand photochemical smog, it's really important that we go over the natural formation of tropospheric ozone in the atmosphere. So during the day, there are nitrogen dioxide in the atmosphere. Just naturally, even if there were no cars, there still would be there, right? And so through sunlight, through a photochemical reaction, right, because it's from the sun, that nitrogen dioxide actually breaks apart into nitrogen oxide and a singular oxygen atom. That oxygen atom reacts with regular molecular oxygen in the atmosphere to give us ozone, or O3. And that ozone is then broken down at night when the sunlight isn't there, right? That nitrogen oxide pulls that oxygen off of ozone to give us molecular oxygen and nitrogen dioxide. So it's kind of this, right? I build it up and break it down and build it up and break it down. And so what happens is that when we add more nitrogen oxides into the mix, things get a little unbalanced. And so the amount of ozone that gets broken down at night is actually reduced in the presence of VOCs, because the nitrogen oxide that the ozone needs to break down is actually more readily bonding with VOCs, and so it's then not available to break that tropospheric oxide down. And so you have this buildup of ozone, or tropospheric ozone, and you have nitrogen oxide and VOCs reacting to give us photochemical oxidants, such as, there's one called PANS, P-A-N, plural, PANS. What does it really stand for? Something chemically, who cares? Right, or hydrogen peroxide is another photochemical oxidant. So all depending on what is available in the atmosphere. You have nitrogen oxide and VOCs coming together to give you photochemical oxidants. That nitrogen oxide is not available to break down the ozone, so the ozone gets built up, and together those photochemical oxidants and the ozone together are what photochemical smog are made out of. And so what does photochemical smog really look like? If anyone's ever been to LA, it's hazy. It's not nice. It's a mixture of primary and secondary pollutants, like I said, right? You have nitrogen oxides and also ozone, and with the exposure to the sunlight, stuff happens and you get photochemical smog. It's highly influenced by temperature. So the hotter it is, VOCs are going to evaporate more, so you have more in the air. With electricity demands, you have an increase in emissions, so NOx emissions, and then chemical reactions just happen more readily with increased temperatures. So if it's hot, you're going to get, you're more likely to get photochemical smog. I'd say that one thing you really want to think about when it comes to nitrogen oxide emissions, you should really be thinking motor vehicles. Like, why is it happening so much in LA? Well, because you have to drive everywhere. Not only does it happen in LA because there are so many cars, but also because of its geography, which we're going to talk about through thermal inversions. So the thermal inversion is basically, well, I'll explain it in a minute, but basically, usually the altitude is decreasing as you go up in the atmosphere, in the troposphere. But a thermal inversion happens when, or the definition of a thermal inversion is when temperature is actually increasing as you go up in the atmosphere, and it traps all the pollution in one place. So if, like I said before, right, usually temperature decreases with altitude, but now you end up with the opposite. So temperature is actually increasing with altitude in the troposphere. And so what ends up happening is that you have this warm layer or an inversion layer that's trapping that cold air from actually rising. And so all of the pollution and all of that air gets trapped and accumulates, and you end up with some sort of pollution event. And so this happens a lot in LA. You have these like pollution events, and it really just kind of stays there until another air mass comes in and blows the whole thing away. And so why does it happen? Well, it could be surrounded by mountains. So usually it's some sort of pocket. So you're surrounded by mountains, like in Mexico City, has thermal inversions all the time. Or in Pennsylvania, you're in the middle of the mountains, kind of in the valley of a pocket, and that inversion layer can occur. Donora, Pennsylvania is actually one of the worst smog incidents in the United States. Like a bunch of people died. And it wasn't photochemical smog, it was actually industrial smog, which College Board doesn't have in their curriculum anymore. But basically, you're burning a lot of coal, there's a lot of particulate matter out in the atmosphere, and people died because there's a thermal inversion trapping it all in there. The same thing happened actually in London in the 1950s. I don't know if any of you watched The Crown, but that actually, that show shows you there's this smog incident where they were burning a lot of coal, and it got trapped in London, and that it was called the Great Smog. But in Los Angeles, it's not surrounded by mountains. It's surrounded by mountains on three sides, and the other side has an ocean. So it's still kind of in this weird little pocket. And that's why Los Angeles actually, right, all of those pollutants stay in the atmosphere around LA until it gets blown away. And so you end up with this haze from the photochemical smog.